thank you to Dr. Yong for this opportunity. So today's the topic of the presentation is about the wireless power transfer, and we'll focus on two cases, bidirectional and dynamic WPT. This is my outline, the presentation outline. The first one, I will discuss a little about the background, and then move on to the introduction of wireless power transfer. And the next one, we will focus on the bidirectional WPT, and then we move on to the LCC-S compensated dynamic wireless power transfer. So I will try. Yeah, I don't really know the background of the attendee here, power or not, but I will try to balance my presentations from the basic one to maybe a little bit more detail about the power electronics. So let's start from the research motivations. As we all know that the important things now in this world, one of the important things in this world is about the climate change. And we understand that the cause of the climate change is about it's because of the greenhouse effect. So many believe that one of the way to reduce the effect of this climate change is by using the electric vehicle, because we can decrease the pollution or the use of fuel-based vehicle, or using like other non-renewable energy. This graph here in the right side is the report from International Energy Agency in the report about the global EV stock, global EV outlook in 2020. So we can see here that they predict that the stock of the electric vehicle in 2020 will be around 140 millions with the stated policy scenario. And if we use the sustainable development scenario, it will up to 245 million EV stock. Of course, this is it doesn't mean that all the stock will be used in the market or will be bought by the consumer, but this number shows that we have a very big potential in the EV technology. And because of the increasing number of EV, the battery proliferation also will be increased in the society. So due to the increase of this EV, actually, we have another problem, because sometimes it will create the surge, power surge, and it will a little disturb the power system actually. So some idea has been proposed to solve this problem by using the EV battery as the storage device for renewable energy during the peak and to support the system during the peak time. So that's why we can say that battery proliferation of EV could be another opportunity for to stabilize the power system by using the vehicle to grid application. Other than EV, of course, there are a lot of applications. Some I put here. The first one is the application of a logistic robot. If you know about this one, Amazon has approximately about 30,000 kiosk robots in their warehouse around the world. This is according to the data in 2016 from Bloomberg. And they use this one to help the worker to move the goods in their warehouse. Another possible applications of robotic here is about the healthcare, especially during the pandemic. maybe you can hear in the news, or you can see many healthcare facilities. They utilize robot to communicate or to deliver food or drugs to the isolated patient. Another one is the use of mobile charger also in medical implant or autonomous vehicle. As you know that autonomous vehicle also is one of the hot topic in these today's. And when we talk about autonomous vehicle, of course, we want that vehicle really autonomous. So even when doing the charging or recharging, we expect the vehicle also will do it automatically. So if you use plug-in charger, maybe it will not possible. Okay. Yes, because of the development of all the technology, we need some charging stations. Right now, the most common one we have is plug-in charging system. And in the future, we expect that the wireless charging system also will be available for EV. I mean, available in public, not only in research or prototype. So if you compare these two systems, the first ones, if we compare the flexibility, of course, the wireless power transfer charging system will have more flexibility because it has no connecting cord. And another one that we need to see about this charging system is about the time constraint, because if we use the plug-in type, it means the car or the EVs need to stop somewhere in the charging station until the battery is full. But if we use like a wireless power transfer, that there is one possibility that we can enable in motion charging. So while the car is going on the road, it can be charged by the wireless power transfer charging. So another one is about the vehicle to grid system. As I mentioned before, the proliferations of battery also can be used as the storage device in the system. So you can see in this picture, we assume that all the power comes from renewable energy like hydropower, solar panel, and also the wind turbine. And then, of course, it will be distributed to the consumer side. And then the consumer side, we have car, industry, home. Even home also can have like a rooftop solar. And in this V2G system, we assume that the battery can charge and discharge to the system. So it will supply the system during the peak time, and then it will charge the battery during the low period. So to enable this kind of technology, we need a bidirectional system. So it enables the power flow from vehicle to grid and also the grid to vehicle. This is one of the potential applications also in bidirectional technology. We move on to the Y dynamic charging. Here I try to compare two types of battery according to their size. If we use a large one, it means we have more energy stored in the battery, and it will have also higher millage. But the downside is it will have a larger size, and of course it will be heavier, more time for recharging, and also more expensive. This type of battery will be suitable for static charging. And how about the small battery? It's the con side is about the less energy storage and then smaller millage range. So that's why it will need a frequent recharging. But the advantage is it will have a smaller size and lighter, and also will be cheaper. And the problem of the small battery also can be solved by using dynamic charging, because during the time when the EV or other technology working, they can also get the power from the charger. So that's about the research breakdown. Now let's move on to the introduction of the wireless power transfer. So this one is the basic one. I hope that everyone will get the picture if you are not in this area. The picture about the wireless power transfer. There are two common types of wireless power transfer. One is the inductive type. Another one is the capacitive type. And when we talk about inductive power transfer, it means we use it commonly in the high power applications. It uses magnetic field as the medium and does not require high frequency devices, and the voltage stress is lower. But the downside is it generates the eddy current loss in surrounding metal material. And for capacitive power transfer, it's commonly used for low power applications because capacitive power transfer usually will have a very low mutual capacitance, so that's why the power transfer also is quite low. Because of these limitations, it requires a very high frequency and high voltage to transfer a larger power. So that's the downside of the capacitive power transfer. But the good one is it's avoid creating the hazardous object in the surrounding area. But of course, this is only one side or some sides of this technology. There are more things to consider if you want to use the technology. The typical system of wireless power transfer can be seen in this picture. As we can see, we have some stages here. The first one is the source, and then the power transfer to AC-DC states, and then to DC-DC states, and then some using pulse regulator, then goes to battery. So this is the unidirectional type, okay? And in this research, our focus is about the DC-DC states. As we can see here, there are two groups actually. Two groups of this. One group is onboard device, and another one is offboard. Onboard device usually will consist receiver coil, rectifier, and pulse regulator, and also battery. And the offboard side will consist of AC-DC converter, inverter, and transmitting coil. Okay, this is the typical inductive coupler. We use two coupler here, only one coupler, one is a transmitter and one is the receiver. So we can model actually this single transmitter like a mutual inductor, and another one we can use also transformer model. And if we use a mutual inductor model, we will have this relationship, like the mutual inductance will be L12 is equal to K square of L11, L22, which is the self-inductance of each coupler. And another one, we have the relationship of the induced voltage to its current and also mutual inductance. As we can see here, there are also voltages that induce in the transmitter side and also in the receiver side. And if we can see in this picture, the voltage that we that we have in the receiving side is P2, and in the transmitter side is P1. Yeah, this is the equations for that voltage. Okay, of course, this is a basic one. If we want to like make it more complicated, we need to consider other things as well. Okay, this is the example. For example, if we use 3 transmitter coils, in this example, we assume that the 3 of the coils are not intersect one another, and also the coupling between the transmitter coils are very small, so we can consider it as one coil in the model. So that's why we can have this type of circuit if we use 3 coils. But again, the assumptions here, we consider that the coupling between the transmitter coils are very small, so that's why we can just omit it from the model. Okay, the basic WPT compensations, we have here some picture, and this is the basics. One is the series compensation, and then we have series parallel, and then parallel series, and also the parallel. And then if we want to find the relationship here, like secondary impedance, load voltage, load current, reflected impedance, and input impedance, we can see it in this table. If we have like series in the secondary, we have the secondary impedance here, so we can use this table to find the impedance and also the reflected impedance and the load voltage. Yeah. Is there any question there? I finish first and then just answer it later.
Yeah, you can continue to present, and then Good. And still have about like 30 minutes left for the presentation.
Okay. The next one is we will focus on the bidirectional WPT. What is the meaning of bidirectional here? Actually, the idea of bidirectional is we can have the power flow in 2 directions. So either from transmitter side to the receiving side, or receiving side to the transmitter side. So that's kind of weird actually. If we say transmitting, it means the powers come from that side. So it means it can exchange the role. It can be transmitter or can be receiver. So this is a series compensated WPT. In this picture, we have 2 types of model actually. The upper one, the A side here is the using the mutual inductance model, and the B1 is using the transformer model. So to solve or to model the circuit here, we usually use the first harmonic approximations. Later, after this topic, I think my colleague Laskar will discuss modified first harmonic approximation. So this one is the first harmonic approximation. So in these approximations, we have some parameters here, and then we have the conversions of all parameters from DC to AC, and also the total voltage gain of the system from the input to the output side. So you can see here, because we have DC as the input voltage, we can transfer or convert it to AC magnitude, and then we have V in AC here, and then the transfer functions of AC to DC is 2 square of 2 divided by 5. And also we can also find the equivalent of the DC load RL here by using these equations, the RL AC n square multiplied to 8 by 5 square. And then if we want to find the all the impedance in the secondary, we can use these equations. And of course, these equations only works in series compensated WPT. If we use another type like series parallel, or we have LCC or LCC-S or double LCC, of course we will have a different model. Okay, and if we continue these equations to find our goal is to find the voltage voltage gain from the input to the output side. We will have this one, like we model it to be simple here, and at the end here we have these equations. This equation here, P out divided by P in, or GL voltage gain, is equal to J omega MRLAC divided by J omega L1 plus J1. Okay, it's difficult to read it here in English. So you can just see here the equations. And I think if we want to dig deep on this topic, you can read this PPT or some paper about this one. And on the right side here is the transformer model here. So there's some difference, but actually the output will be the same. The output will be equal. Okay. Usually, when we do the design of WPT, we need to check the voltage gain of the circuit. So that's why the next one is we plot this equation here. We plot these equations here, and then we can see the relationship between the voltage gain and also the load and also coupling coefficients. As we can see here, when we plot the equations with different load, so you can see here the load is the load varies here from 10 ohm to 70 ohms. And if you see in that curve, we have two independent frequencies actually, which is labeled here as WH, and another one is WL. So we can utilize this one if we want a stable output voltage. It means the output voltage is not heavily dependent on the load. But if we want to change something, also we can utilize also these 2 points here. Okay, and another figure here in the right side is the relationship between the voltage gain with coefficient. Yeah, I think this is a coefficient K. So as we can see here, when we have a different coupling coefficients here, like from 0.15 to 0.2, this point here, I mean the independent frequencies here is moving. Like here we have a moving independent frequencies here. Like here we have in this point, but if we have K equal to 0.2, we have it in this point. So it's really depend on the coupling coefficients of our coupler. Okay. Next one, I'll move on to the considerations. As we can see here, when we do the design for WPT, we will have we will consider many things. One is the efficiency. As you can see here, we consider the loss of the whole system, and to have optimum value, we need to consider about the power loss in the power states, and also this one is affected by the resonant current. So if we have a larger magnetizing inductance, we will have a smaller resonant current. But if we have smaller magnetizing inductance, we will have a higher resonant current, which is contribute to the total loss of the system. So that's why higher coefficients, coupling coefficient is always better. But in some application, of course, there is limitations, there is consideration. So we need to consider all of that. And how about the operating frequencies? As we can see in this graph, as you can see here, when the frequency increase from smaller one to the higher one, you can see that the voltage gain increasing until this point here, and then after that the gain will be decreased. So the question is, how can we choose the frequency if we have this kind of system? So if someone choose between omega minimum to omega minimum 2 here, we'll have trouble, because when we have when you use like a controller here in this point, for example, when we have a closed loop system, we start from here. So the controller will be programmed to increase the frequency if the voltage is lower from the reference. But when the frequency always increase, for example, and then meet to this tipping point, it will decrease, and the controller also will continue to increase, because it thinks I need to increase the frequency to get a higher voltage, but actually it will be decreased. So that's why in this types of system, we need to limit the frequency. So here, the best choice is by using the omega minimum 2 to omega maximum. So this is the better choice of the switching frequency here. As we can see here, this is in one side. So if we decrease the switching frequency, the voltage obviously will be decreased. So the program or the controller will not send the wrong comment to the system. So that's about the switching frequency selections here. Okay, next we move on here to the hardware considerations. Yeah, when we want to design this type of system, we have to design coupler, the coils, and also we have to choose the compensation parameter. In this example, we choose the capacitor as the fixed parameter, because the consideration is usually the parameter of capacitor is fixed from the market, so we cannot easily change it, compared to coupler that we can easily change by reducing or increasing the wire length. So this is some example of the gain plot here. I have a lot of line here that shows the effect of the self-inductance here. Okay, so here also we need also to consider how much the coil inductance we need when we design the system. If, as we can see, if we have a larger L here, the voltage gain will be more sensitive. You can see we have a steeper ratio here compared to using 100. So that's again depend on the design and the requirement. Okay. So this is the full schematic of the system that we have built before. We have here the transmitter side, or we can say this one A side or B side because we want to test it in bidirectional mode. So in A side and B side actually are identical. So the system in the A and B almost the same. Okay, so this is the parameter here. We have the output power is 3 kilowatt and input voltage 400 volt and output voltage we target 400 volt, and coupling coefficient also we limit between 0.15 to 0.3, and operating frequency also we limit between 81 to 89 kilohertz, and the coil dimensions is around 700 millimeter, and the air gap is larger than 200 millimeters, and full load efficiency will be larger than 95. That's the target. And for the compensators, we have resonant here, capacitor 10.24 nanofarad, and another one 10.23 nanofarad, and we use the Wi-Fi here as the communications, for communications. Okay, and we have this coil before, and this one is for 3 kilowatt, and I think we don't have this anymore in lab right now because it already changed to 8 kilowatt. Okay, this is the data about this coil. It's around 0.43 millihenry, and we try to make it identical, but of course it's really difficult to get it have the same value. Okay. Okay, and the magnetizing inductance here we have around 65.9 microhenry, and we measure this one in 1 kilohertz frequency. And after doing some tests, we have this key waveform here. So you can see in the left side is for 210 millimeter air gap, and another one is for 200 millimeter air gap. And as we can see also here, we have also the GPS waveform conditions to confirm that the system works in GPS. That's why the efficiency of the system is quite high. So this is the efficiency of the system at 210 millimeter coils. In this we have the highest efficiency is around 96, more than 96 I think. So because the side A to side B is almost identical here. That's why we can say that the system works perfectly in bidirectional mode, can work perfectly in bidirectional mode. Okay, this is the conclusions of the first one that I think I just need to read one here. The maximum efficiency is was about 96.8, performed at 210 millimeters separation with power flow direction from D to A. Now, efficiency also slightly decreased for a larger coil separations and has a slight difference for the difference for power flow direction. Of course, we have the data for 250 millimeters. It shows a lower frequency actually, but I don't include it here. Okay, do I have how many minutes I have?
Okay, you have 5 minutes left.
Okay. Okay. And this one is for dynamic type. In dynamic type, we have we use different kinds of compensator. We have LCC-S here, and we follow the same step from the previous one. The difference here, all the maths are quite a little different, and also design also is a little different. So because of the time constraint, I think I don't want to discuss this one. So let's move on to the voltage gain here. We have the voltage gain here. This is the equations. How we have these equations, of course, by calculating it from the top, and then we have this one. And this is the, I want to show the voltage gain here. If we use LCC as compensator, we have a different voltage gain versus load here. If in the previous one, if we use series compensation, we have two independent load frequency, but here we have only one independent load frequency. So that's why we can say this system is better work in a fixed frequency mode here. Okay, this one another plot from that gain. We want to see how it affects how the mutual inductance affect the gain, and we can see here it also decreased almost linearly, I think. Okay, skip this one, and this is the parameters we use in the system, and this is the picture and the hardware we developed before, and this one is the whole experimental setup. We measure it, and then this is the some key waveform we have, and this is also show the switching transition. The difference here with the previous one, we don't have a clear GPS here because some it still have some cross section here between the voltage here. Okay, this is the waveform under different output power, and yeah, this is the experimental efficiency. The largest one we have is 91.2, 91% efficiency. And if we compare the displacement to its efficiency, we can see here that because we have 3 coils, there are 3 peaks of the efficiency. So this is the one thing that need to be improved in this research, how to make this one more flat. Okay, so this is the conclusion. As has been shown before, the theoretical analysis and simulation experimental research also show good matching one another, and also the maximum efficiency that we have is around 91% at 1.5 kilowatt. But the air gap is around 5.5 centimeters. And also, it is a strong evidence that the fixed frequency is suitable for this kind of topology. And for the future works, maybe using the regulated output, and also for larger air gap also can be used in the future. So this is conclude my presentations, and thank you for your attention. Give it back to Dr. Young.
Okay. Thank you very much for your very good presentation. Yeah, about the wireless power transfer. Yeah, with many kind of like topology and also like the good analysis. And also like there are many questions.
Oh.
Yeah, many questions.
Okay, I hope I can answer it. Okay.
Yeah, most of the questions now are from the student from University of Ho Chi Minh City, University of Technology and Education. So yeah, I'm sorry, I will speak in Vietnamese a little bit.
Okay, yeah. No problem.
Các em ở trường sư phạm kỹ thuật có muốn đặt câu hỏi trực tiếp tới diễn giả luôn không? Okay, it's okay. So I can help them to ask, to transfer the questions to you. So most of the questions related to the design of the wireless power transfer, like they ask about the good distance from the car to the surface, the road surface. And then another question is like, can the wireless charging system be harmful for the human health or not? Yeah.
So I answered it first?
Yeah.
The good one, the separation distance, right, between the charger, the transmitter to the receiver for EV. Usually it will follow the height of the vehicle. For standard ones, usually it will be around 20 centimeters to 30 centimeters. That's depend on the vehicle that we use actually. Another one is about the safety. I think the safety of the wireless power transfer. Yes, it can be harmful if someone have a metal inside her body or holding some metal things, and then suddenly go to the charging station, I think. But many research also have tried to solve this problem. So the system will detect the foreign object on the top of the transmitter, and then if that object is not a vehicle or receiver side of the vehicle, the system will not turn on. I think that's the proposed solution for this problem.
Okay. And follow to that questions, like they ask about if the distance between the car and the road is larger, so how to solve that problem?
If the distance larger. Okay. Yeah. I maybe, to my understanding, maybe the question is like, if we have a larger separations, and then how can we transfer more power or the same power? Maybe that's the question. Am I right?
Yeah, right. Yeah.
Okay. That's we can say like a constraint, I think. When we need to transfer the same power with different distance, we need also a larger coils. So because we need to maintain the mutual inductance, or we can do like a controller to catch up with the larger separations. So the solution for that one, it can be hardware-based solution by increasing the size, and also it can be software-based solutions by using the controller to compensate the distance. I think that's my answer for that one.
Okay. And the next question is like, what is the frequency for the transceiver? And like, because like we have the radio on the or the signal on the car, so will it affect to the transceiver frequency or not? Like the noise will affect to your transceiver or not?
Right now, the common frequency for inductive power transfer is about 81, I think, 81 to 89. That's a common frequency. And as I know, that's also the slot that we have that is not occupied by other technology. So that's why most of the researchers using this frequency. And if we use higher frequency like 100 to 120, maybe that will interfere with other frequency like radio or maybe Bluetooth. I don't really know which one, but of course there is some standard. Maybe I cannot say that's a final standard, just like standard under development to limit the frequency for wireless power transfer. And if we use a very high frequency like 1 megahertz, also is very common use in the wireless power transfer. But I don't have knowledge on this standardizations, I think. So right now, the most common one we have in this application is for lower frequency is around 80, and for higher frequency is around 1 megahertz. That's my answer for that.
And like another questions, like when we have the wireless power transfer for the car, like we're charging the car with the wireless power transfer, so that one will take longer time than the traditional one using the wires to charge the car. And
yeah,
like, okay.
Yeah, that's also possible actually.
So
we cannot say that wireless power transfer will solve the longer time charging, but when we consider like a dynamic charging, like when the car is moving and then it can get recharged from the transmitter side, like we have say maybe we can say like a charging lane, say like that, it will help. It will help to reduce time. But if we use static wireless power transfer, it will be the same. Maybe it will be longer if the efficiency of the wireless power transfer is not good enough. But I think one of the most important issue in this development is the battery is not ready for faster charging. I think that's the issue. So that's another topic. That's another we can say not power electronic business, maybe material science or chemistry. I don't know. Maybe that's one problem that needs to be solved. Yeah. Any other question? Where is your?
can I ask a question?
Oh, yeah.
In your presentation before, thank you for your nice presentation. It is a good review for the wireless power transfer technology. And I have a question about the comparison between the series resonance and LCC-S topology. The LCC-S topology cannot change its switching frequency. Then how can we control the output voltage in LCC-S topology?
We can change the frequency, but it doesn't look good. I mean, not in optimum conditions. My purpose to that kind of problem is by using the pulse regulator or so we control the output later, and in for the transfer power from transmitter to receiver, we use a fixed frequency. I think that's one of possibility. Another one, maybe use a phase shift, maybe also can help to control the circuit.
Then, according to your material, the series resonance has higher power conversion efficiency compared to the LCC-S. Then, can I ask your personal opinion that what is the main advantage of the LCC-S topology?
One of the advantages of LCC-S technology is it's stable or fixed transmitter current, so it doesn't affect the, how can I say, fixed, like independent transmitter current to the load in the receiver. So that's one of the advantages of the LCC-S compared to series.
Thank you for your answer.
Thank you, Mina.
Okay. There are still many questions.
Oh, do we have time?
Yeah. Hey, Phạm Thế Tiệp, do you want to ask the speaker directly?
Em cảm ơn anh Dũng. Thank you for your presentation. I'm Tiệp. I'm from EVSCR from University of Science and Technology, and I have some questions for you. First, at slide 14, you saw that there are some compensation configuration. So how can you calculate the capacitor? And is that depend on the coupling coefficient? The first
Slide number 13.
Yeah.
13.
14.
14.
Yeah.
Let me check first. 14?
Yes. Yes. So how can you calculate the capacitor?
This one?
Yeah.
Can you share the screen?
Oh, I have stopped it. Sorry about that. Number 14? 14 or 40?
14.
14. Oh, should be going up. This one? Sorry, this one?
Okay. Yep. Okay. Can you show me how to calculate the CP? And it depends on the coupling coefficient.
CP. Oh,
Yep.
I think that this is okay. I know. Yeah, that's depend on the CP. We can calculate depend on the coupling coefficients, because from the coupling coefficient actually we know the self-inductance and we know the leakage inductance, and then also we need to define the frequency of the system. So by using all these parameters, we can calculate how much the compensation capacitors that we need from the system. That's the way we calculate it.
Thank you. But when the coupling coefficient is changed,
Yes.
So how can you tuning that?
Right now, some people try to tune this one by using the, we can say, switching things, like they change the capacitance when the coupling changes. So it will have the same, it will regulate the transfer power. And another one is, okay, I read only about the one, the switching capacitance, they use that one. But if we use only one capacitor, of course, we cannot change the capacitor. But we can compensate it by using, like, we control the frequency if we use the variable frequency control. And if we use a fixed frequency, maybe I don't really know how to solve if we use a fixed frequency, but for this case, we can use the variable frequency.
Thank you. Can I ask you only one question more?
Yeah. Sure.
Yeah. I know that some standard about frequency, like 1885 kilohertz.
Yes.
What do you talk about the vary frequency? I think we have to do by standard.
Right. You're right. It's the fixed frequency, or the standard is around 85, but I think it's still okay to change a little from that one, because of course we have a small band, frequency band, that we have freedom to use, I think, because right now I don't know if there is a rule that say that we cannot use variable frequency for WPT. So I think it's okay as long as it is not interfere with other systems. I think that's the most important.
Okay, thank you. I have some question. I have another question, but I think I do not have time to ask. So thank you so much for answering me. Okay.
My pleasure.
Thank you.
Okay. There are still many questions, but we are running out of time. So okay. So let's see. Can you have to ask the speaker directly after the, like, send a text message or anything, like after the webinar, or can
he can send email, I think.
Yeah, it's a good way to do it.
Yeah, I can. If I can answer, I will try to answer. Or maybe I can just give some requests.
Okay, thank you. Yeah, thank you for your very nice presentation.